Hi everyone, so now we are going to see in this video how delta H can be calculated for an experiment. So you know that delta H can be calculated from Q, and Q can be calculated from the formula MC delta T. Now if we do an experiment where a reaction produces a change in temperature, we can calculate delta T. And if we know the mass of the reagent being used, and usually the mass would be the mass of the limiting reagent, we can have Q divided by number of moles of limiting reagent, we'll get delta H. Now this can be done by a calorimetry experiment. So calorimetry is a technique used to measure change in enthalpy of reactions, and changes in enthalpy are determined by finding changes in temperature. Now this is one of the setup of a calorimetry experiment where we use a polystyrene cup or a coffee cup, which is going to act as an insulator to keep the heat of the reaction mixture inside the system. So usually it helps to prevent heat loss to the surroundings. So here you have the reaction mixture, for example, copper sulfate, aqueous, and zinc. So usually this will lead to a displacement reaction producing zinc sulfate and copper. Now in this displacement reaction, heat is liberated. Now the heat liberated leads to a change in temperature, so delta H can be calculated. If we use excess of zinc, this would be in excess, and we know the mass of copper sulfate that we used, we can apply that equation. Q is equal to MC delta T. So let's get into more details in this experiment. So in this experiment, we're going to have a few assumptions. So we are going to assume that there is no heat loss to the surrounding. Now the coffee cup, like I mentioned, acts as an insulator preventing heat loss to the surroundings. But there is no guarantee that it's going to do that. So it's very difficult to measure the heat loss from the system. So we're going to assume that the heat loss to the environment is negligible. Now this is one assumption. Other assumptions is that the copper sulfate solution is made by adding copper sulfate solid in water. That's why it's aqueous. So aqueous means dissolved in water. So we are going to assume that the copper sulfate solution has the same specific heat capacity as water. So we are going to assume that it's the same value. That's another assumption. We are also going to assume that the mass of the copper sulfate solution, so here let's say we are using 25 centimeter cube of copper sulfate. Now we are going to assume that the density of water is 1 gram per centimeter cube, meaning that the 25 centimeter cube of copper sulfate is going to weigh 25 grams. So this is another assumption. So we are assuming that 25 centimeter cube of copper sulfate will mean 25 grams of copper sulfate solution. Another assumption is that the container, this polystyrene cup or coffee cup, has no heat capacity. We are assuming that this cup is not absorbing any heat from the reaction. And we are also assuming that there is no heat loss to the surroundings, that all the heat is maintained here, and that any temperature change is being detected by the thermometer here. Now, because there's a lot of these assumptions, these will lead to a specific kind of error in this experiment. And this type of error is called a systematic error. A systematic error is a kind of error that comes from a problem in the experimental procedure, or faulty equipment, or improper use of equipment. This is going to lead to systematic error. Normally, a systematic error can be corrected if the source of the systematic error is known. In this case, all these assumptions lead to an error in the experiment itself. And this systematic error will cause the experimental value to be very different from the theoretical value. Let's say delta H is supposed to be 60 kJ per mole. Experimentally, you're only going to get 40 kilojoules per mole. It's always going to be less than what is expected because there is a large amount of heat which is actually lost to the surroundings that we cannot cater for. So this difference in value leads to a high percentage error, and if you remember, percentage error is calculated by this formula. So this formula, when you apply this, you find that percentage error is quite high. It could be around 30 to 40% difference in experimental and theoretical value. Now, this percentage error, unfortunately, cannot be explained only by errors due to equipment. Every equipment has an uncertainty, so that's why you calculate percentage uncertainty of equipment. So in this case, you would use a measuring cylinder to measure the copper sulfate. You would use a thermometer to measure change in temperature. So the uncertainty of the measuring cylinder and the thermometer is not able to account for the high percentage error. So in this case, the systematic error is because of the experiment, because of the heat loss to the surroundings and to all these assumptions that are made. Now, when you add the zinc to the copper sulfate, temperature goes up. So how do we do the experiment? So firstly, we're going to measure the volume of the copper sulfate. So you can either measure volume or mass. So let's say we measure the volume of the copper sulfate, we pour it in, and then we put in the thermometer. You're going to measure the temperature of the copper sulfate at regular time intervals until it stabilizes. So usually this is going to be room temperature. So this is what we are monitoring here. This is the initial temperature of the copper sulfate solution without any reaction happening. At this point here in time, so let's say we're measuring time every half a minute. So let's say here at 2 minutes, I add in the zinc. When I add in the zinc, the temperature normally should go high, extremely high at this point. But it is not possible for us to get that highest temperature, that maximum temperature. We cannot measure it because it is supposed to be instantaneous, but it's never instantaneous. So during that delay, the substance itself is going to lose heat to the surroundings. So we are never able to get that maximum temperature. So what happens when we add the zinc here? We're not going to measure any temperature. After adding it, after half a minute, I'm going to measure the temperature again. So then I keep measuring the temperature every half a minute until we have a constant rate of cooling here. So this is the cooling section. The temperature is going down. So you're going to keep on measuring temperature until you have a cooling section. Here we are assuming that rate of cooling is constant. And then once we have this graph, we are going to extrapolate the graph. This part here, so we're going to draw a line at the part where you have the constant cooling rate, and you're going to extend the graph like this, like I've drawn the dotted line. At the 2 minutes when we added the zinc, we are also going to extend here, to extrapolate here. This temperature, where these two lines meet, this temperature indicates the maximum temperature, maximum instantaneous temperature that should have been recorded, but that we unfortunately cannot record in practice. So this would be the T2, final temperature, highest temperature reached. And this here is the T1, initial temperature of the system. The difference in the two will give you change in temperature that you can apply in this formula Q is equal to mc delta T. So the T is the change in temperature, which is given by maximum instantaneous temperature minus the initial temperature. C is the specific heat capacity of water. M is actually the volume of copper sulfate, and because we are assuming density of water to be 1, so then the volume would be equal to the mass. So that would be the volume of copper sulfate used. Now from the value of Q, we can then find delta H. Let us see this in a question. So here, excess of iron is added to copper sulfate. This is the concentration of copper sulfate. This is the volume of copper sulfate. And then you add iron to that copper sulfate, and the maximum temperature rise was 7.5. So this is delta T. So from this, I can apply the formula Q is equal to mc delta T. Mass would be equal to volume because we are assuming density of water to be 1 gram per centimeter cube. So this is 100 grams. So 100 centimeter cube, which is equivalent to 100 grams. We are assuming. So M is 100. C is the specific heat capacity of water. We are assuming that the specific heat capacity of the copper sulfate is the same as water. And delta T is given 7.5. This will give you the value of Q in joules, because this is in grams, this is in joule per gram per Kelvin. From the value of Q, I can get delta H. Now I'm going to convert Q into kilojoules because delta H has to be in kilojoule per mole. Now from this, delta H would be minus Q over N. Now what is N now? Number of moles. If you remember your mole concept, number of moles is concentration times volume. So concentration is given, volume is given, this is in centimeter cube. I'm going to convert to dm cube. So I divide by 1000 to convert to dm cube, and this is the number of moles of copper sulfate. And why I'm finding the number of moles of copper sulfate and not that of zinc? Because zinc is in excess. It says excess of iron powder. So number of moles is number of moles of limiting reagent. So then I apply the formula. This is the value that I get, but I'm going to change this to the proper SF. If you look in the question, this is here, this is given to 4SF, this is to 3SF, and this is to 2SF. So answer should be to the minimum SF or one better. Minimum SF is 2SF, so you can give your answer to 2SF or 3SF. I am choosing to give to 3SF, so this is the answer that I should report to the correct SF here. So this experiment requires a graph like this to be made.